talk briefly about particle size distribution, and then we'll go to particle shape characterization. So particle size distribution, so I'm giving here, right? So everyone guess what sample is? Maize. Okay, very close. Holes. What's that? Wheat, exactly. So it's from wheat milling. So first break, wheat milling process. See, if you go to any wheat flour mill, they will have at least 6 to 8, mills or grinding machines. Okay, this product is from the first break. They call this first break. It's the first grinding. So you can see the product that you are getting, top to bottom. Right? So pieces hands till you can see flour will be close to 140 micron, 150 micron size. Okay. Do you know how much at least not in Indian condition, not in Indian context, but in US or Canada, can anyone guess how much product goes waste in a grain processing or grain handling industry? Any guess? 20%. 20%? Okay, that's a very good guess. Any other guess? This is again general, it's not something related to particle size distribution, but any other guess? One more. 30%, okay. So not even close, so it's 0%, okay. So almost everything is made into a product, okay. If you, for example, if this is a product from, first break mill or first break, so you get, lots of different products, you might know farina, wheat flour, different, grades, and then the top bran and stuff will go to, animal feed, the feed industry, okay. But if they are milling whole wheat, you might have seen whole wheat products, right? So then what they do is they don't mill the whole wheat per se, but what they do is they mill separately and then mix them together. Because milling everything together will be very difficult, because bran will break differently than starch and protein. So they mill separately the bran and then make it into fine particle and then mix it in the same proportion like in a wheat kernel. Okay, that's how they make the whole wheat flour and whole wheat products. Okay, so you'll see whenever we deal with the product, there will be always any at least the granular material, you will have a size distribution, right? They are not of uniform size, right? But if you're talking about glass beads or spherical beads that we use in necklace and those will be identical because they are manufactured, right? Manufactured for the same size and shape. But natural products, will always have a distribution. Okay. So how many type of distributions that you can think of? Do you know how many different types of distributions we use mathematically or statistically? What's that?
Statistically, we can say Poisson distribution.
Okay, Poisson's distribution. Okay, normal Gaussian distribution. Okay, there are many, right? Normal, log normal, what is that? Suddenly it's not coming to my mind, that we use for, milling of particles. There is another distribution that we use, okay. But there are, different types of distribution or mathematically that we use to describe the particle sizes, right. Particle properties, again, I'll show one example too. They change, it might be from the same origin, same product, but based on the size, their property will also change, right. At least you can imagine surface area will change, its shape will change, its texture will change, etc., right. But again, we'll talk briefly about the particle size distribution here, but you take any property value, it could be coefficient of restitution, or it could be density, or it could be any value, you will always have a distribution, okay. It's never, it's the same value, okay, or same, same constant value, okay. So how does it affect, particle size distribution? Obviously, you know about porosity, right? So if you have uniform same sized particles, then the porosity will be higher, right? You know that, right? But if you have a mix of particles with different sizes, then the overall porosity will be lesser, right? So again, I'm showing you, this is simulated, image here. if it's of different mixtures, in general, the porosity is high, but if you have a large varied mixture with, a distribution of particles, large size to medium size, small size, etc., then their porosity, overall bed porosity will be smaller. Okay. How it affects, again, this porosity will definitely influence transportation and packaging, right? Any compacts, it could be pharmaceutical tablet or it could be food compacts, etc., right? So how does this porosity or the particle size distribution affects the transportation and packaging cost? How does it influence transportation? What's that? What will increase?
Cost.
For what product? Same size, yeah. Same size, if the particles are of same size, what you will be packing is more air, right? And you would have seen those chips packets, right? Lace and stuff, it will be more air than chips inside, right? And I had a chips packet in the guest room where I'm staying here, I opened it, there was like 4 chips and then full of air in that packet, okay? So that's, again, you'll be, if it's of same size, you'll be, shipping more air, but if you wanted to ship more product, you'll have to have a wide distribution in those particles, right? But, that's one, again, advantage, you can ship more, right? The density or the packing, will go up. But what will be one disadvantage of shipping, a non-uniform or a particle with or a powder with, distribution? Any thoughts? I briefly talked about that yesterday, if you remember. So what happens when you transport? It shakes, right? So what happens when it shakes? What's that? Separate, segregation, right? So it leads to segregation. We talked about it yesterday, right? Anyone saw any video on YouTube on the nut effect I talked about? No one. Okay. The Brazilian nut effect on the segregation. So if you shake, larger particles will come to the top and small particles will go to the bottom, right? So that that can also lead to segregation if it's a wide distribution. But it definitely influences your transportation and shipping. Again, I'll skip this one. So again, particles of different size, they again pack. This is an example from a simulated example of packing in a large container. Okay, so if you have a wider distribution, then you can almost close all the pore space or white space within the large particle, right? Then your packing efficiency will go up. The tendency to pack will also go up, or tightly packing will also go up. But again, segregation will occur if it's free flowing powder. But if it's cohesive, then there will not be any segregation, right? It almost like if it's cohesive, there will not be any segregation of particles. Okay. So now not going into the detail, but it's a porosity ratio, and based on the size of the particles, I'm giving all those references too in the end. Okay, if you wanted to learn more about these papers, you can read from them too. Okay, so in general, again, particle size, if it's wider, then again, wider distribution will decrease the porosity, okay, or the bed porosity. Okay, so a larger range of size again increases the strength of the compacts. When you are making, anyone working on compacting powders, compacts? No one. So how does a distribution increases the strength of compacts? So if it's of same sized particle, okay, you are compacting 2 different particles. One is with same size, one with wider distribution. Okay, so as I mentioned, if it's wider distribution, then it increases the compact strength, right? So how a wider distribution is increasing the strength?
So different particles will fit
Okay.
each other.
Okay, exactly. So do you know what happens when you compact powders? The mechanism of compaction. you would have learned in undergrad, but you might have heard about adhesive bonding, cohesive bonding, right? So those bonding will occur, right? So when you are compacting, those bonding occurs, and if there is less air space, then there will be higher bonding. So there will be more or higher surface to surface contact that increases the bonding between particles. So higher the bonding, higher the strength of the compacts. Okay. Decreased flowability and decreased permeability. Permeability, obviously, if there is less pore space or void space, air cannot move through, right? So that's very important, important problem when you are working in grain storage or large, storage structures where you have to aerate, aerate the grains or products to improve their or increase their shelf life. Okay. How does flowability? Flow is bulk movement of the material. How does wider distribution affect flow of powders? Come on, give quick questions. Okay, we are already late, behind the schedule. Quick answers.
Due to coarse particles, they have large contact area.
Coarser particles, more than coarser particles, will be finer particles. Okay, so finer particles, again, there will be more contact, or finer particles will fill in the void space of coarser particle, and there will be more contact to contact between the particles. So when contact to contact between particles increase, what does increase? What is that? Cohesion. You would have learned about van der Waals forces, right? Van der Waals interaction, etc. So those van der Waals interactions will be higher since the interparticle distance is very low. Okay, so that affects the flow behavior of bulk powder. Okay, so just a brief introduction. We'll go talk about types of distribution. Okay, so when you talk about particle size, what are the two common distributions we usually plot? You would have seen almost all of you would have done during undergrad. Pi? For particle size, we may not use pie chart, so normal, but how do we plot? What's that? You would have seen, right? So there will be two different plots, so usually one is like this, it could be a normal distribution, but there will be one like, right? So now you know what are these different distributions, right? What are those?
One in log scale and another.
What is that? Someone said. Oh, make it stronger? Oh, okay. I will try, but but I will not be using a lot. But so what is this distribution called? Normal, not normal. We will go into the mathematics, the general name for this distribution. No, that's normal. We'll not go. We'll go into math and stat. In a minute.
Volume versus size.
No, that's you can plot volume. Good guesses. Any one final guess? Thought. If I know, that's very simple. You will not. You all know. Okay, this is frequency distribution, right? You all know, right? What is this called? Cumulative distribution. So these are the two distributions we generally plot, right? Frequency and cumulative distributions, right? So do you know why we plot these frequency and cumulative distributions? Or what differences does it make? Why we have to plot frequency or cumulative distributions? Any thoughts? Okay, keep thinking, but we'll go through that in a minute. Okay. So again, as we talked about, almost all, not most, almost all powders does not have identical sizes. Except if you are manufacturing, you might have a tighter, distribution without a tighter, particle size without distribution, but commonly we present as either frequency or cumulative distributions, right? So same particle size distribution, but you can plot them as, either frequency or cumulative. We briefly talked about this, right? So if you are using microscopy, it will be a number based distribution. If you are using light or laser diffraction, then it will be a volume based distribution. And then again, surface area or by mass if you are, using sieving method, right? So again, type of instrument that you are using to measure the particle size will define the type of, not the type of distribution, but the distribution you are plotting, either number or volume or surface area, etc. Okay. So in general, when we get particle size measurement, we try to plot a histogram, right? Okay. So histogram, so at any specific interval, so what is the number of particle or what is the weight of the particle on each sieve, and then plot a histogram of that, of that distribution, right? So it's an example again, a couple of histograms. One is again a fraction of particles in that size, and then it's the same same particle size, right? So same powder, but you can see two different distributions, right? So as again I've written the notes here too. So depending on the bin size that you use, okay, so the distribution might differ in a frequency distribution. Okay, clear? So if you are using a smaller bin size, then you might get a different distribution than if you are using a larger bin size, you get a different distribution in histograms. So what do we do to avoid this type of effect? What's that? No, there's one more in it. Still in frequency. We haven't gone to cumulative yet. So this again talking about histogram, right? Okay. So to avoid that, we use the bin size, same bin sizes, divide them with bin sizes and get the frequency distribution. Okay. So when you plot frequency distribution instead of histograms, you get irrespective of the bin size, you get the identical distributions. Okay. So when you are measuring particle size, make sure you're not plotting histogram but plotting frequency distribution. Okay. So if you're plotting histogram, you might end up with some error, okay, depending on the bin size. Okay. So again, as said, the frequency distributions, when you use when you use different bin sizes too, the distributions will be very closer. Okay. So in frequency distributions, again, you can define them in mathematically too, right? So if you have a distribution, again, you can get the fraction of particles in specific range sizes, right? Within specific range, again, for example, if you wanted to quantify the amount of particles within this range, it will give again the total number of particles within this with the total number of particles that comprise the entire powder. Okay. So again, n is the total number of particles and n is the number of particles within that size range. Okay. Simple math, right? So always you know that the frequency distribution area under this frequency distribution will be 1, right? So the area under the curve should be 1. If you are not getting 1, then there is some error, or maybe you lost some powder during sieve analysis. Okay. If you lose some, then you may not get an area of 1, but okay. So cumulative distributions, again, it's adding everything together, right? So it's cumulative based on the size, right? So in general, we use this to quantify. Okay, so my particles, I have like 50% of particles below this size, and 50% of the particles are above this size. So just to give a quantification or quantified result, a number of particles that is within the bulk. Okay. Again, here the area will not be 1, right? So it's a cumulative. Again, mostly used to get the undersized particles or oversized particles within that range. Okay. Any questions? Okay. So again, these are again simple equations, simple simple equations to calculate both the frequency and cumulative distributions. Okay. So cumulative distributions, it's very easy to get, 10 percentile, 50 or 90%, you would have seen D10, D50, D90, etc., right? When you are measuring particle sizes using any instrument, usually it gives D10, D50, D90, etc. That means, 10% of particle will be in that range, 50, 90, and again, in that specific ranges, okay? D90 means the almost 90% of the particles will be below that size, okay? Again, that's the way we use this cumulative distributions to get those, sizes, okay? Mostly for undersized, again, if it's cumulative for oversized, the curve will be reversed, like it will be falling from the top to bottom, right? Okay, so you can use for both undersized and oversized calculations, okay? Any questions? So in general, frequency, again, frequency distributions, it's easy to obtain the mode, median, etc., but cumulative distributions are, easier to get this D10, D50 and D90. You may not be able to get that from frequency distributions, but from cumulative distributions, okay? Again, you can plot either undersized or oversized. Oversized is 1 minus q, q is the total particles. Then the graph will look like, almost reverse of the undersized, okay? You all know that, right? Don't know? You know or don't know? You know, okay. Any questions? Okay. So this one, example, we don't have to calculate. But I was planning to do do the calculations by you, but are you guys ready to do the calculation and plot it? So this, again, particle size distribution in similar, specific range. So you can calculate the bin width, mean diameter, mass fraction on each sieves, cumulative, mass fraction coarser and finer, or undersized and oversized, okay? And then you can plot all of them together, okay? So this gives this the, frequency distribution, and this is the finer, and this is the coarser, curve for, that specific example or specific distribution of the powders, okay? So you get different information from these three, graphs, right? So you can see, mode, it's very easy to find from frequency distribution, right? For, finer distribution, you can easily get D10, D50 and D90 very easily, and, from the cumulative distribution, okay? Both for finer and coarser distributions, okay? Any questions so far? So how many of you done this, like plotted frequency cumulative distributions? No one? Undergrad during your BTech? Maybe you might forgot, yeah. So I'm sure you all would have done that, during undergrad, okay. So again, types of distributions, we briefly talked about this, right? Number, mass based, volume based, area based, etc., right? So depending on the measurement method, the type of distribution that we obtain will also be different, right? So again, you can convert from one distribution type to another distribution too. For example, if you have a mass based distribution, okay, that you get by, from sieve analysis, but you can convert that into a volume based distribution too, okay. So I very briefly talked about that yesterday, but what is the factor that we have to use to convert from one distribution to, anyone remember? What's that? Someone said something. There is a, it ends with factor. It's a shape factor, okay. So use a shape factor to, again, convert that from one distribution, but it's, strongly discouraged, because when you use shape factor and convert from one distribution to another, your, I too briefly mentioned yesterday too, your error will also multiply, if it's from volume based, then the error multiplies by 3 times, cubes, okay. So, just some example, if it's a number based distribution, you get, the total number of particles from the, again, smaller q indicates frequency distribution, okay. It's if it's uppercase letter, then it's a cumulative distribution, okay. If you see any distribution, if it's lowercase letter, then it's always a frequency distribution, and uppercase letter indicates cumulative distribution, okay. Again, from those distribution you can get classify the powders. Someone said air jet classifying yesterday, right? So that's some of the principle that we use when we classify and powders. At least couple of you are working on protein separation, right? So that's one common principle that we use for those classification, okay, based on size. And if you know the distribution, you can classify them, okay, now how many number of particles I wanted to separate, or how much volume of the particle I wanted to separate, or even with specific some different surface area, I wanted to separate particles with low surface area or high surface area, etc. Okay, so that's the basic fundamental that you will apply when you do your research on classification. Okay, any questions? Yeah, go ahead. Yeah.
Mm-hmm. Will that be same in all the cases? Like if you convert from number to volume, there will be one subfactor.
Yeah.
Will it be the same if you convert like?
No, that's a great question. So the shape factor will depend on the type of measurement you are doing. Yeah. So for number based, there will be a different shape factor. Volume based, there will be a different shape factor. Okay. Not sure we didn't. I know I didn't include those in there due to time limitation. Okay. But you can calculate shape factors from the particle size calculations that we talked about yesterday. Okay. I might have briefly have it in the shape lecture, but we'll see. Okay, the particle shape lecture next one. Okay, not sure though. Okay, so how does it affects? For example, this is again from Malvern. For the same particles, if you are using different distributions. Okay, so this for the percentage of mass of space debris. Okay. So if the space debris again, size of particles, you can see smaller particles. Smaller particles are in higher number. Okay, so their distribution will be different, but percentage by person mass, you can see the larger particles will have a higher frequency or higher percentage, right? So if you are using different distributions, you might your results will also be different. Okay. So again, as we know, the type of instrument that we use will define the type of distribution, but comparing different distributions may not give the same results. Okay, just as an example. Okay, any questions? Is that clear? How many of you are still with me? Go ahead, any questions? Are most of you with me? Some are nodding, some are okay, I'm here, maybe, may not be, right? But I skip a lot of math behind this. I know we have some agriculture students. So do you guys study math?
Sir, we study statistics.
Statistics, yeah, we don't study math, right? Okay. So I skipped most of the math, but again, if you are interested in learning more, I will be teaching this class online from January. Okay, but you will have to pay some fees, money to Purdue, so it's not free. Okay, but I'll be still going little in depth when I teach, since this is only 4 days, right? I teach this as a regular class at Purdue, but again, I teach that online too. So does particle shape change with size? As the for most of the particles, the shape also changes with size. That's why it's very difficult to use the shape factor to convert from one distribution to another distribution, because the shape changes. For example, smaller particles, you might get more uniform shaped material. It's not always the same case, okay, but smaller particles may have more uniform shape than a larger particle. Okay, I'll go back to our, example of wheat milling, right? So do you know the shape of a starch granule? What is that shape? Spherical, not usually, always, okay. Starch, starch is always spherical, right? So, but, what, do you know the size of starch granule?
80 microns
80?
to 80 to 100.
It's usually 30 and above, 30 to 50 or 60, at least in wheat starch, it could be from, might be other starch, might be larger. What's, yeah, pulses might be a little larger, yeah. But what is the particle size of wheat flour? Close to 150, right? Close to, it's not, around that, okay. So, but the starch granules are spherical, it's about, approximately say 50 microns, right? But wheat flour is about 150 microns, right? So, what will be the shape of a wheat flour particle then? Will it be spherical? Not always, right? Not always. Most commonly, it's not spherical. Since you will have protein fragments, protein attached to multiple starch granules, so their shapes will be different. So, just giving an example. So, with the change in size, their shape will also be different. So, that is why it will be difficult to use, shape factor to convert from one distribution to another distribution. Okay. Any questions? No. Okay. So, we will go through characterizing distributions. I think this is the last part of particle size distribution lecture. Okay. So, what are some of the information that you can get from these distributions? What are the stuff we calculate from these distributions? You all would have done, but might.
Mass fraction, diameter.
Okay, mass fraction, diameters, what else? Characterize the distribution. So, overall distribution, what are the values that we calculate? Yeah, mass fraction, said, you can calculate coarser, finer, etc., right? What else we calculate? Or determine, not calculate, we determine from the, distributions. What about median, right? So, we get the median of distribution, right? What else? Now, I gave you one answer, right? So, what else we calculate? Median, then what else? Variance, exactly, that's very good. Variance, then? Like, I have all those in the PowerPoint, but I just wanted to see how many of you remember, okay?
Standard deviation.
Standard deviation, yeah, variance, usually we use variance to characterize distribution than standard deviation, sometimes, yeah, okay. What else? Come on. So, what are some of the statistical parameters that you can think of? Mean, mode, median, then, okay. What else? What's that? Come on, be louder. As I said, there is no wrong answer in the class, okay. Okay, so am I asking too many questions? Does your brain hurt by thinking? No, right? Okay. So again, lots of information, that's what my, older daughter uses, when we ask questions and when she reads a lot, then she comes back and says, oh, my brain hurts, okay, I cannot study anymore. Okay, that's the example I'm using here, okay. So again, mean, variance, etc., but we'll go through some of, the other values too, okay. So mode, it's very easy to obtain from a frequency distribution, right? So that's the largest value. It's very easy to get. You may not be able to get this from a cumulative distribution, right? So both frequency and cumulative distributions are important, and it will help us to characterize or to know more about the particles that we are dealing with. Okay. Again, median we can easily get from a cumulative distribution, right? 50% of the particle, that's the median value, right? So that's easy from a cumulative distribution. Okay. Then again from cumulative, as I talked before, you can get D10, D90, D50, etc., right? So 10% of particles that's undersized, or 50% of particle that's undersized, etc., right? So, either coarser or finer. This is finer distribution. If you're, plotting a coarser distribution, then you can get 10% of particles closer, coarser than that value, etc., right? So, it's clear now, right? So, you can get all this information, then, span you might remember, right? So, span of the distribution, so that we can get from the cumulative distribution. So, that's from, D90 and D10 over, D50, okay? That gives the, width of distribution, okay? And also coefficient of variation, again from the standard deviation and mean, but that can give, sometimes we use, but again, it's not very common, but mostly we use, the variance that I will talk about in a minute. But you can calculate the coefficient of variation too, right? So what, I'm just asking one question, maybe you can get the answer later on, okay? So why do we use coefficient of variation instead of standard deviation? Any thoughts? So coefficient of variation is standard deviation over mean, right? Sigma over mu, as the formula indicates, right? So why not we just use the standard deviation? Why to use coefficient of variation?
Can you give the percentage how much it deviated from the
Close, but not the exact answer that I'm looking for, okay? But again, think about it, okay? I'll ask the same question when we come back, okay? During the next lecture.
more precise?
Why it's precise? It's very close to it's precise, yeah. You don't know. You said you don't know. You find out, okay?
Because it's correlating both the standard deviation and the mean.
Yeah, that's what why, Okay, think about it, okay? Since we do not have any quizzes, so let me, make you a little bit, or, you all use ChatGPT, right? AI, right? How many of you use AI or ChatGPT? Okay. It's very easy now, right? So if you're, it's very handy when you do literature search, right? So you just give a command, it brings all the literature that's published, around that, in that topic, right? So you don't have to work a lot. How many of you use AI to write papers? You use? Okay.
All literature,
What is that?
all literature work written by the AI.
Literature review? Okay. I'm not sure about the rules, at least in the US, if you're using AI, that's plagiarism still to write.
Sometimes rules is there, but if you do something according to rules, you can.
Oh, okay. Yeah, that's, if you're following, but I'm,
according to you.
okay, okay.
Analyze this.
So what, many of my students also use AI, but what I suggest usually is, ask them to write original draft first, okay, then use AI to edit for grammar.
With the help of AI tool, we can get number of ideas.
Yeah, sure, getting ideas, that's very useful tool, right? So again, mean, we can calculate different means, right? So arithmetic mean, quadratic mean, cubic mean, etc., right? So the type of mean that we calculate depend on the application, okay? So all these means will, again, applications will be different. Type of, the method of measurement will also, quantify different means, okay? Most commonly, we calculate arithmetic mean, but very common in sieve analysis to use to calculate harmonic mean, okay, 1 over x, okay. And then this is a general notation just for your information. So if you see some particle sizes like D23 or D32, in general it indicates again two notations. So the first notation is the type of mean, okay. So for example, if it's 2, then it's a quadratic mean. and then R is a type of frequency distribution. Okay, again, what type of distribution you are talking about. Okay, so that's the general notation that we use for particle sizes. Okay. Variance, again, variance we very commonly use for quantifying this frequency distributions. Okay, so again, larger variance, the distribution will be spread wider, right? So if it's small variance, then the distribution is much tighter. Okay, and I'm not going to the calculations. Again, from the average individual particle sizes and from their mean values, you calculate the variance. Okay. Skewness is very commonly used, right? So it gives more information about the type of particles, whether we have smaller group of smaller particles or larger group of smaller particles, etc. For example, if the skewness is 0, that means it's more uniform distribution, almost all the particles are of same size. Okay, but it's kind of negatively skewed. That means if the skewness is 0, again we calculate the skewness from the individual particle sizes and the average. If the skewness is negative, that means there is a higher portion of larger particles. Okay, and if the skewness is positive, greater than 0, that means there is a higher portion or proportion of smaller particles in the mix than the larger particles. Okay, so again, if the skewness is 0, then it's almost the normal distribution. Okay, so the particles are almost uniform. Okay. Kurtosis, you might not see a lot of this use of kurtosis in characterizing at least particle distributions. So if the kurtosis, again using the individual particle size and the mean mean particle size, for a normal distribution the kurtosis value will be 3, and if it's greater than 3, it's much tighter distribution, almost uniform same sized particles in the mix. But if it's less than 3, in general again the distribution will be wider. Okay, so if you have a mix of small and large particles, then the kurtosis value will be much smaller. Okay, not going into the calculations yet, I just giving some information here. So different size distribution, again you might get mono distribution, that means of same particle sizes, or bimodal, polydispersed. Uniform you might not see, except if you are manufacturing particles like extruding of same size, then you might see a mono distribution. Okay, I'm sorry, uniform distribution. But very common is the bimodal distribution. For example, we will go back to the wheat flour. The starch particle sizes are 30 to 50 micron, but the overall flour will be about 140, 150 micron, right? So you'll get a very commonly you get a bimodal distribution with large number of starch and a large amount of protein and starch combined particles. Okay, but polydisperse is also common if you are for any type of powder. Polydisperse a distribution is also common. Okay, and again, so most of the time this distribution is limited by the method of milling or sieving that you use. If you are using, for example, a hammer mill, the screen size that you use on the hammer mill will define your distribution, right? So what's the opening size, and type of opening will define this type of distribution. Again, particle breakage, and if you see more agglomeration, then you might see more bimodal distributions too. Okay, any questions? Just quickly going through all the statistical parameters. Okay, so again just summary. So almost all the powders will have a distribution, right? So they are never of uniform size, but if you are having some frequency and cumulative distribution, we can understand more about the powders. We can characterize them better. For it could be either for classification or downstream processing, or for shipping and handling. If you have a good knowledge on or good understanding on the size distribution, then you can define your process accordingly. Okay. Any questions? That's almost the last slide, and again there are lots of standards, ASTM, ISO standards for calculating this particle size and particle size distributions. Okay, and some references. Okay. Questions? Ask some questions. One or two. No questions. You already asked too many questions or tired of asking questions? Go ahead, Prakash.
So
Yes.
mean,
Yeah.
you showed as denotation in the
Hmm.
suffix part. So how we can denote it, like K, comma R.
Mhm.
So how the number is specifically to give 3, 2, 1.
Oh, okay. So might be I didn't include that. So, for example, I think volume-based distribution is number-based distribution is given a notation of 0. Okay, and then volume is 3. I think surface area is 2, and then mass-based is given m. I think there's no number. I think it's given m, notation of m as mass. I can bring that. I think I don't have that in this slide deck.
Sir,
Go
what is
ahead.
the purpose of calculating harmonic mean?
Harmonic mean? Yeah, that's a good question. So, it usually depends on the process that you are uh, it's mostly based on mass, right? So maybe shipping calculations, etc. might be could be used, but we generally not use harmonic mean. So mass based or sieving based, that can give this harmonic mean. Okay. I do not know a specific example, but I'll try to find out. Okay.
So when we have to use which kind of mean? Means there are specific area where we can use arithmetic, where it's quadratic.
Usually you don't have to worry much about those. In general, what you calculate is volume based. You'll have to keep in mind the type of size you are calculating. Is it based on volume or is it based on number or my mass? That's a major thing. But commonly, again, we use this arithmetic mean, and calculate the particle size, average particle size. Okay. Arithmetic and geometric mean also is common. Okay. So why do arithmetic means more or less if the distribution is uniform, arithmetic mean will be okay, it gives a good average value. But again, if you have a wide distribution, like for example positively skewed or negatively skewed, then I showed an example of particles, space debris, right? So you'll have to include on the different factors, right? Number of particles in each category. Okay. Then you might use a geometric mean so that you bring in all the particles together, and if the distribution is much wider. Okay. So if it's tighter, then usual common is the arithmetic mean. Okay. Cubic mean, I think it's mostly applied for surface coating and all. It's volume based, right? So surface coating, dissolution, etc. might cubic mean might be more useful than arithmetic mean. Okay. And quadratic mean, again, mostly for compaction problems they might be using these quadratic mean calculations. Okay.
You
Go ahead.
said that distribution that decrease the probability.
Yeah.
So how we can
Particle size distribution, yeah.
like large?
Yeah, large, yeah.
So how can we means by research in research how can we show those things?
Sure.
How we can relate particle size distribution and flow reliability?
So we'll talk about powder flow. I think I will have some examples there when we talk about powder flow. Okay. So there are lots of research work done on particle size distribution and flow. Okay. So there you can do some simple simulations too, like DEM, take some different particles. So any of you know DEM other than you? Discrete element method modeling. There was a lecture yesterday. Okay. So those will be easy and helpful to understand some of these. You generate some mix of particles and then just simulate vibration. It's easy to do in DEM for like 100, 200 particles. You'll see that effect on flow and effect on segregation, etc. Okay. But we will talk about. I think we will briefly talk about particle size distribution effect on flow when we talk about flow. You can do simulation, you can do measurements, that will show.
Experimentally, sir, how we can
Experiment, shear cell analysis. Shears. Do you have a shear cell here? Shear cell. Ring shear tester. Ring shear tester, again we will talk about that then experimentally. There are different methods. Ring shear tester is very common. You might know FT4 powder rheometer. Some of you might have heard. That's very common, to measure the flow of powders. Okay. Does that answer your question? Again, we will talk more about in flow I think on Thursday. Okay, tomorrow or Thursday. What is it?
Sir, I have heard like flowability index, something like that.
Oh yeah, flow index. Yeah,
How to get some insight on that, sir?
we'll talk about that on powder flow lecture. Okay. It's more than flow index. It's called flow function. In one of the slides yesterday, I would have mentioned flow function. So that's what the parameter that we measure using shear tester. Okay. Any other questions? Good questions. Yeah.
Sir, what if a particle has same volume but different shapes? So which model will be more suitable for that?
Which model means which?
In these models, which model I can use for that? If particle have same volume or same size but different shape?
I don't. You mean DEM model or?
No, these distribution.
Oh, the distribution you can. Okay, I didn't include all the type of distributions. Okay, so we briefly talked about normal distribution, right? Normal. I think you will have to plot and see. Normal distribution, log normal. Distribution. Log normal distribution should fit most of the wider distribution. Okay. If not Rosen-Ramler distribution. Okay, that might also fit. But that's the name I was trying to remember. Rosen-Ramler, if you are especially working on milling, Rosen-Ramler might give better idea, or particle breakage, etc. That will give better idea of your distribution than a normal or log normal. But for simple distribution, a log normal distribution will almost fit most of the particle size distributions. Okay. Any other questions? Okay, so if not, let's take how much time break you want? 1 hour? No. Someone said 1 hour. No. 5 minutes, 10 minutes. I'm not sure when. Will the tea be ready? You don't know. If the tea is ready, again you can have tea and come back. If not, let's take 5 minutes break. Okay. So the amount of research on food powders compared to pharmaceutical solids is very small, very minimal. Not many people are working in that area. So, and DEM, for example, discrete element method. Do you know how it originated?
Yes, sir. Sir, see.
Yeah, Kundal and Stack. Okay, but they were working on soils. There's soil fracture, soil mechanics. But that's how discrete element method modeling was developed. But who applies more? It's pharmaceutical industry. So agriculture industry is slowly picking up on using DEM, but not like pharmaceutical industry. They use a lot. Mining industry, they use a lot. So, okay. Any other questions? Okay, you can just Google CP3 and you'll see, CP3 Purdue, you'll see all the information about, particle group at Purdue. Okay. And again, we do have a, if you visit Purdue, I will take you to our lab, so we do have a very excellent characterization, particle powder characterization lab, that I currently manage. Another TNA student is the temporary lab manager for that, he's still looking for a permanent lab manager. The one he left recently. So we do have almost all type of characterization instruments. So if you take particle size, we at least have like 5-6 different types instruments to measure sizes, size, shape characterization, density characterization. Flow, for flow we have like 4 or 5 different instruments to characterize flow of powders. So, but most of the instruments are listed on the website. If you check, see. And some people work on modeling, both discrete element and finite element modeling. Okay, so that's also a big area of research again. Do you know why we do modeling? Why do we depend a lot on modeling, mathematical modeling?
First of all, to avoid some costly prototypes.
Okay, yeah.
Second one, impractical things like if some closed some machine is there, so we can detect through model.
Oh, you can give to them. Yeah. Oh,
Detect that
thank you.
part which we can't do practically.
Sure.